what I was asked to talk about was variation in silage composition, and most of what I'm going to talk about is that, but you need to remember what I'm saying is applicable to all feeds, including TMRs, but I am going to concentrate on silage. What I'm going to talk about is data from a very large project we've been conducting in Ohio here for over 3 years, and we've generated a tremendous amount of data, and we've learned some stuff we weren't expecting to learn. What I have here and what I'm going to be showing you is real data. This isn't simulated. This is real farm data from commercial dairy farms in Ohio or from different areas in the U.S. And I'm going to be concentrating on the two silages I'm going to be talking about is corn silage and hay crop silage. And in Ohio, most of our hay crop is alfalfa, but the species is irrelevant. The principles are the same. But here's an example of a farm data. We go out and sample, in this case, haylage, and in this case, we analyze NDF. And we get a number, 45% NDF. Then you go back to that farm after a certain period of time and take another sample. And in this case, it changed appreciably from almost 45 to almost 55%. And what you need to think about is, why did it change? And there's several reasons. Very often people, nutritionists, this is what they think. It's the silage really changed. I have to go reformulate my diet. It was at 45, now it's at 55. I need to change the diet. That's possible, but that is not the only thing that could explain that change. It could be you just are a bad sampler, and I don't mean you as an individual, but in general, we just have a bad sample, and what you're looking at here might be just sampling error. You don't know. The third possibility is the lab made a mistake. And again, you have no idea which of these three are the reason. It's most likely all three of them are combined. But the point is, you can't just assume when you get a new number that it's a real change. It might not be. If it's sampling error or lab error, that doesn't mean the silage changed. So don't think it's just silage composition. What this data actually was from a single farm daily samples. So this just shows you how much your data can vary up and down on a given day from a given farm. This project we did, one of the projects where we went to 11 commercial dairy farms near Worcester, Ohio. We sampled silage 14 consecutive days. Each day we took 2 independent samples. And what I mean by independent is we'd go out and say they had a bag of silage. We'd take 10 or 20 handfuls of silage, put it in a bucket, mix it up, take a subsample, throw that silage away, then go back and take another 10 or 20 handfuls, mix that up, and take another sample. So these are independent samples. And we took 2 every day for 14 days. We took these to our lab, and we conducted 2 assays on each sample. So we did 2 NDFs, 2 proteins, etc. And so what we end up with is 504 samples, or 504 numbers for each nutrient. And it doesn't, the math doesn't quite come out right because some days a sample got missed. And what you see in the green box there are the means, which are not important for this seminar. So I'm going to hardly ever mention the mean value. What I'm going to talk a lot about is variation, or in this case, standard deviation, SD. So we had about 500 dry matters for corn silage, but they're not the same. The standard deviation was 5.2. So the question we were asking is, why didn't we get the same number? Why didn't we get 504 37%? Why was there variation? And the same question for NDF and for starch. So what we did, the way we set this experiment up, we can actually, what we call, partition the variation. And so because we had 11 farms, we can separate farm-to-farm variation. Because we had multiple samples, 2 samples per day, we can determine sampling variation. Because we had 2 assays per sample, we can detect or determine analytical variation. And then whatever is left is what we call true day-to-day variation. This means the silage really changed. So again, multiple farms, from each farm, 2 samples, from each sample, 2 assays. And what I'm showing here is a partitioning the variation. The blue bar is the percent of total variation due to farm. The red is what we call the true day-to-day. The green is sampling, and the purple is analytical. And with the exception of corn silage ash, which I can't really explain, but with the exception of that one, the rest of them all do about the same thing. You can see very clearly farm-to-farm variation is the biggest source of variation. About 80% of the variation we see is due to farm, which I think everybody would expect. But you'll see that sampling, this green one, is quite big. And in most cases, it's bigger than the true-to-true variation. And then in most cases, analytical variation is very, very small. So what it means is the lab is not likely to be the reason numbers differ. So farm-to-farm variation was a huge proportion, which just means you have to sample every farmer's or every client's silage. You can't use silage data from farm 1 to balance the diet on farm 2, and that's news to no one. It also means you should not trust a book value. There's too much variation for silages. I don't have time to get into this, but for some feeds, this is not true. For example, corn grain. You are better using a book value for corn grain than actually analyzing it, because the farm-to-farm variation is so small. But again, I don't have time for that. What we were interested in is not farm-to-farm variation. We knew that was big, so we're ignoring that for the rest of this talk. What we wanted to know was how much does the silage vary within a given farm. You can see the data here. Again, the means are not important. These standard deviations are the within farm standard deviation. They're a lot smaller than the total standard deviation. A lot of people are not familiar with using standard deviations, so I just want to show an example here with corn silage. The standard deviation within farm standard deviation was 2.3. And we can use that to calculate risk and probabilities. This is the mean, 30, let's say 33. So with this standard deviation, what it means is on 5 out of those 14 days, the starch value in that corn silage could be less than about 30%, or it could be more than 35%. 5 out of 14 days. And you have to think, would that affect your formulation strategy? And in most cases, yes, it would. So some of these within farm standard deviations are still substantial and nutritionally important. So we broke down the within farm. This is just showing corn silage. And what I want to show you is, in most cases, the true day-to-day variation over this 2-week period is actually a minor source of variation. By far, for fiber, starch, and ash, sampling error was the biggest source of variation. So if you'd get 2 different NDF values for corn silage in a short period of time, it's more likely to be caused by sampling than to be a true change in the silage composition. Dry matter is the exception. Over this 2-week period, dry matter was more likely to be a true change than a sampling error. And again, this makes sense because it rains. If this is in a bunker silo, it's going to get wet, and that's a true day-to-day change. So there's more reasons for dry matter to change day-to-day than for NDF over a short period of time. So what I tried to do here is put this into terms that are more user-friendly than standard deviations. And so I just took 2 nutrients, corn silage and hay crop. I'm looking at just NDF and dry matter. This column here is the average range due to sampling. So let's just use an example here. I sample corn silage I get 35% dry matter. What you really should think about is that's really 35 plus or minus 2 units, because that's the sampling error. NDF would be plus or minus 4 units. And you need to think, why would it be so different? Why wouldn't the sampling error be about the same for NDF and dry matter? Well, you have to think of what you're sampling. With corn silage, you're sampling pieces of cob, pieces of kernel, pieces of stalk, pieces of leaves. Those different pieces have, the dry matter of those different pieces are much more similar than the NDF of those pieces. If you get a few extra pieces of kernel, very low NDF, that will have a big effect. Or if you get a few extra pieces of cob, very high NDF, that will have an effect. For the hay crops, dry matter and NDF had about the same sampling variation. And this is, again, because now it's much more difficult to selectively sample a haylage. The pieces are smaller, they're wetter, and they tend to stick together a little bit better. Now, this other two columns, this column here is this experiment we've been talking about, the true day-to-day variation over a 14-day period. Another part of this experiment, which I haven't talked about, was we went and sampled silages over a 12-month period, but we only took samples once a month. So this is a true variation over a year with monthly sampling. This is true variation over 2 weeks with daily sampling. First thing you need to notice, over a short period of time, sampling variation is as big as true day-to-day variation. So again, in short changes in short terms, think sampling is just as likely to be the reason. So don't rush to make a change in your diet. The other thing to look at here is for hay crops, over a 12-month period, the true variation is more than twice what it was in this short period of time. And that makes, again, perfect sense. Over a 14-day period, we're likely going to be in a single cutting, maybe even a single field. Over a 12-month period, it's going to be multiple cuttings, maybe multiple fields. So you expect much more true variation over a year than over 2 weeks. Look at corn silage, though. The dry matter over a 12-month period, the variation is much, much bigger. And again, that makes sense because these silos, a lot of these silos are bunkers, and they get rained on. So the dry matter changes more over time. Look at NDF. It's virtually the same variation over a 2-week period compared to a 12-month period. And then look at sampling. In other words, over a 12-month period with corn silage, changes in NDF are just as likely to be caused by sampling as it is to be real. And too many people assume any change in corn silage is real. They go reformulate, and they end up with a poor, unbalanced diet because the silage really did not change. And this is an example of a farm. This is starch, but the NDF is pretty much just the opposite. And these are daily samples for 14 days. And what this illustrates is the real risk of sampling error. If most people do not sample silage every day, they may sample silage once a month or once every few weeks. But if you happen to formulate, if this is the sample you took and you formulate on that, you're going to have a very bad diet, because it's clear that the starch in this corn silage is probably 25%. But if this is the only information you have and you formulate it on assuming it's 15, you've introduced a tremendous error in your formulation. So this illustrates the real risk of sampling variation, in that you formulate a diet based on poor information. How do we get rid of sampling variation? Well, we can reduce it by taking good samples. You're never going to eliminate it, but you can reduce it. And the other way we can minimize the effect of sampling variation is to take multiple samples and average. First part I'm going to talk about is just good sampling practices, and a lot of this is common sense. Here's an example if I go to sample, this is a bunker, and so I'm on the top of this bunker, which you should never be because of safety issues, but if you are, when you took this handful of sample, all you're sampling is this little bit right here. You're not sampling here, and you're not sampling here. You've got a very poor subsample. Whereas if you would remove a lot of this silage, this is corn silage, so different silage, but if you'd remove a bunch, this bucket load might represent many, many feet across to that silo. So this handful very likely represents a much bigger portion of that silage. So mix as much as possible before sampling. And then take progressively smaller subsamples. One, again, you never sample from the face of a silo because of safety issues, plus you get a lousy sample. So you deface, or however you're removing the silage from the silo. This now is pretty well mixed. So again, you would take bucket loads of this and subsample from the bucket. Put that into there, and I'm going to do that multiple times. I'm going to take this bucket then, which will be full, dump that out, mix it, and then take a subsample. Instead of just taking a few handfuls from here, which doesn't represent the entire silo, it's much more likely now that this bag will represent much more because I'm taking smaller and smaller subsamples. The exception to this is hay. Never, ever subsample hay. The bias is huge. But silages, if you do it correctly, subsample. And then just think about what you're doing to this sample. Here are 3 ways you could transfer the silage from the bucket to the subsampling bucket. You can use a scoop. You can use your hand with the hand facing down, or you use your hand with the hand facing up. This is absolutely the worst because as I move my hand from here to the bucket, you're going to be losing things. You're going to be losing small pieces. And the nutrient composition of small pieces is different than the nutrient composition of big pieces. This is the best because I'm not losing any pieces. This is a good compromise. But think of things you do to this sample that biases particles. Here's corn silage. This is with the Penn State three-stage particle separation. This is the top. This is the medium, the middle screen. This is the pan. This is the NDF and starch. This top fraction is mostly stalk, leaves, and maybe some cob. So very low in starch, high in fiber. This is the pan, which has got a lot of the kernels, crushed kernels. Low NDF, high starch. So if you sample in a way that you reduce the amount of little pieces in your sample, you're going to get a silage sample with elevated NDF. If you sample in a way that you lose big particles, you're going to get a sample that says it's low in NDF. So again, think of ways you can reduce sampling bias. And sampling bias is introduced by losing specific particles. The other way you can do this is average. Take multiple samples over a short period of time and average them. We think you need 2 or 3 samples. Here's some data here. The red line is a single daily sample. The blue line is the average of 2 daily samples. Both of them ended up over this 14-day period with exactly the same mean, which we would expect. But look at the standard deviation. Single samples, 2.6. A mean of duplicate samples, 1.4. The range with single samples was 9 units. The range with the means, 5 units. So with these multiple or these mean samples, what you do is cut out extremes. So if this was your single sample, you're going to formulate assuming it's 42. If you took 2 samples and average them, you're going to formulate assuming it's 38. So you reduce risk. So again, a mean of multiple samples is much better to formulate than a single sample. The last thing I want to talk about is how can we manage true variation. You manage sampling variation by taking means, but how do you manage real variation? I'm going to talk briefly about 2 experiments we conducted. One is where we changed the silage dry matter abruptly, mimicking a rain event. Again, because of time, I can't go into detail, but basically we fed cows for 21 days. The gray boxes here are 2 3-day periods in which 2 of the treatments we took the silage, we put water on it the night before, changed the dry matter by 10 units, decreased it, and then fed it to the cows. All the other times here, all 3 diets are exactly the same. What you're looking at is deviation from the control, so I didn't plot the control. And you can see during the times when these cows were fed the same diet, they did about the same thing. The 2 treatments, one is what we call unbalanced. We fed wet silage and we didn't do anything. We just fed more feed. So this, because of the silage is wetter on a dry matter basis, these cows were actually getting less forage. The blue line is where we rebalanced. So we adjusted for the change in dry matter, so we increased the as-fed forage, and so on a dry matter basis, everything was the same. In all cases here, we fed more feed. So when we started feeding wet silage, we increased feed delivery, and that's a key component here. We fed more. So if we look at, I'm not going to go too much into 2 different bouts because generally they did about the same thing. And I'm not going to spend too much time talking about the treatments because generally they did the same thing. But if you look here, the first day these cows were fed wet silage, they increased their intake, but they didn't increase it enough. It took them 2 days to realize that this stuff got so much wetter that they had to eat more. Then what we found was extremely interesting. This is the day after. And the day after, so now these cows are back to being fed regular corn silage, but they continued to eat more. It took them a day or 2 to realize it got wetter, and it took them a day or 2 to realize it got drier. Very consistent. All cows did this. This was as fed. We're used to, the thing I want to emphasize again is that during these wet bouts, cows were overfed. They never ran out of feed. We're used to talking dry matter intake, so this is the same data, but now it's dry matter intake. I said the first day they didn't eat enough, so dry matter intake was significantly reduced. The second day, it was not. It took, by the second day, they ate enough, and they're eating more. But now look at the day after. Dry matter intake, sorry, these are pounds, I forgot to convert this, but 1.5 kilos more dry matter intake the day after. So remember, if you feed wet silage, they're going to eat more when it turns dry for a short period of time. And the way you take advantage of this is you make sure cows are overfed. The other thing, if you'll notice, if I said there was not much difference here between the 2 treatments, but if anything, actually rebalancing the diet was worse. In other words, adjusting for dry matter and changing the forage to concentrate ratio actually was worse than just feeding more feed for these short terms. This last experiment, we had a control, which was constant forage NDF here, 25%. And the treatment is we reformulated this diet every day, and this is a predetermined pattern that on one day it would be 28% forage NDF, another day here it's 23, another day it's 21. So we randomly picked this pattern. So one set of cows were fed a variable diet, one set was fed a control constant diet. What we found was absolutely no effect on performance. And these were high-producing cows, more than 45 kilos for the mature cows in this. What we did find was that there was a significant increase in day-to-day variation in intake and in milk production. But over time, over the 21 days we did this, it averaged out. A key component to the protocol we used is that we always overfed cows. going to try and back up here. So on these days when these cows were fed high fiber, they ate less. They did exactly what the book said. But then on these days when they were fed lower fiber, they ate more. And because we overfed, on these days when they were fed a better diet, they could eat more. But if we did not provide extra feed, then on these days when the diet was actually better, they would have run out of feed and they couldn't have compensated. So a key thing here is on variable diets, you have to feed more so that when it's on the days it's bad, you throw away feed, but on the days it's better diets, you allow these cows to eat more. There's an economic cost to that, but that's one way to manage variation. So to wrap up, sampling is a substantial source of within-farm variation for silage. Also for TMRs, I didn't have time to go into that. Because sampling error is so high, you should have very low confidence in a single sample. I'm not saying taking samples and analyzing are a waste of time, and some people get that out of this slide, out of this talk, and that's exactly the opposite of what I mean to say. What I'm saying is we need multiple samples and a mean. Do not formulate diets based on a single sample, 2 or 3 samples. But don't over average. Some people just keep average. They'll collect this data and they sample every couple of weeks and they just keep a big average. And what that does is it makes things too smooth. Real changes happen. So what we're suggesting is you collect data, you sample at least once a month, and then you average 2 or 3 samples. So you have a running average. You say you sample in June, you go back and sample in July, you take that average and formulate. You sample again in August, then you might kick out the June sample. So a running mean of 2 or 3 samples, that's what you do, and that will prevent you from making a big change when the diet or when the silage really did not change. We found, and we've done more experiments than what I can talk about here, but substantial changes in dry matter and NDF did not affect production of the cows if we allowed these cows to eat. So if the diet is highly variable, NDF, and we've done this in protein, we've done this in fat, if the diet's highly variable, one way you can manage that is you feed more. What that means is you're going to be throwing away feed on these days when you feed more and they leave it, it's thrown away, but then on the days when they eat more, they can produce the milk they lost on the day before. So if you suspect high day-to-day variation in diet composition for whatever reason, first try and figure out why it's varying and control that, but in the meantime, increase feed delivery rates. That'll help the cow compensate for variation. And with that, I thank you for your attention, and it was my pleasure to speak today. Thank you.